In this video, I'm going to show you how you can get from here to here. So we've seen our interest rate problem. If you compound it continuously, it will lead you to this. In fact, it doesn't have to be 100%. If something grows by a certain amount of a percent, let's say 13%, if you compound it continuously, for some reason this thing crops up. So in nature, this thing crops up quite a lot whenever you have something that grows by a percentage of an amount, and if you compound it continuously, this thing will crop up. But then we used mathematics to obtain this. In fact, these two are exactly the same. So in this video, I'm going to show you how you can get from here to here, because for us to obtain this, in some of the early videos we looked at this bit here. This bit here will lead you to this. So now in this video I'm going to show you how you can get from here to here. But before I do that, let me just illustrate something to you. You've I'm expecting you to recognize this. This is a very important limit. When sin x over x, the limit as x heads towards 0 equals 1. We've seen this before, and I'm expecting you to know this. So whenever this bubble and this bubble heads towards 0 and they're on par with each other, then you can say yes, the limit is 1. So for example, if you look at this thing here, you've got x squared and x squared, and as x heads towards 0, this bubble will head towards 0, this bubble heads towards 0, and they're on par with each other. So yes, you can say this whole thing here equals 1. And then if you look at this, this thing here, as x heads towards 0, this bubble will head towards 0, and this bubble heads towards 0, and they're both on par with each other. So you can say yes, this thing here does indeed equals 1. If you look at this thing, however, you've got two bubbles here. As x heads towards 0, yes, this bubble is heading to 0, and yes, this bubble is heading to 0, but they're not on par with each other. So you can't say this equals 1. You just can't say that, because yeah, this bubble is heading towards 0 and this bubble is also heading towards 0, but they're not on par with each other. So we had a proof. We proved that whenever these two head towards 0 and on par with each other, then you can conclude that it does equal 1. But here they're not heading towards 0. They're not on par with each other as they're heading towards 0. So we can't conclude that this equals 1. We just can't conclude this. If you look at this thing down here, hang on. If you look at this thing here, you've got a bubble here and a bubble here. As x heads towards 0, this bubble heads towards 0, this bubble heads towards 0, and they're both on par with each other because they're exactly the same. They're heading towards 0 and on par with each other. So you can conclude that this equals 1. If you look at this one here, you've got this bubble being exactly the same as this bubble. As x heads towards 0, this bubble doesn't actually head towards 0. It actually heads towards -9, and this bubble heads towards -9. So you can't conclude that this equals 1. So you can't conclude this because this bubble is not actually heading towards 0, even though x is heading towards 0. This bubble is not heading towards 0. This bubble is not heading towards 0. In order for you to make use of this, this bubble has to head towards. These two bubbles have to head towards 0 and on par with each other. Well, this one here is not heading towards 0 at all. It's actually heading towards -9. So we can't say this equals to 1. Okay, let's look at this one here. You've got a bubble here which is exactly the same as this bubble here. As x heads towards, even though x is heading towards 3, even though it doesn't always have to head towards 0, even though it's heading towards 3, this bubble here is indeed heading towards 0, and this bubble is also heading towards 0, and they're on par with each other. So we can conclude that this equals 1. This is perfectly fine. This does indeed. The limit is 1, even though it's heading towards 3. So it doesn't always have to head towards 0. Okay, let's look at this one here. This one here, you can't conclude that this equals 1. You can't, because this bubble here, even though this bubble is heading towards 0, even though this bubble is heading towards 0, they're not on par with each other. We can't conclude that this equals 1. That they're not on par with each other. So it's similar to this one here. This one's heading towards 0. This one's heading towards 0. This bubble here heads towards 0 faster than this one here. So you can't conclude. Well, I hope you get the idea. So now let's go back to our original aim. Our original aim was to, hang on. Our aim is to get from here to here. Okay, so we've got to somehow convert this to this and convert this to this, and then it's not heading towards 0, but it's heading towards infinity. So this thing here occurs in nature. This thing here occurs in nature. We used mathematics to obtain this. So now we're going to try and get from here to here. So let's start from here. So hang on. Okay, so let's start from here. So now the trick, this is a trick that we use quite often in maths. We're going to say let x equals this thing here. So now times both sides by n, so that will then give you this. Now divide both sides by x, so now n is on its own. So if you look at this thing here is exactly the same as this. So we can put n into here. And then if you look at x, we can then put this into here. That will then give us this. So, but the thing is, we need to take care of this. We need to take care of this. So look what happens up here. Look what happens when x is heading towards 0. What is happening to n as x heads towards 0? So let's look at this. We want to investigate what happens to n. As x heads towards 0, 1 divided by something that's approaching 0, this whole thing here would just get bigger and bigger and bigger. So really, up here you've got x heading towards 0, but in terms of n is actually heading towards infinity. Because look, as x heads towards 0, as this thing here heads towards 0, n is actually getting bigger and bigger and bigger. So to translate this, we need to say that n is heading towards infinity. So hang on. So now we are at this stage here. So in effect, n is actually heading towards infinity. So now we can imagine this as being a bubble and a bubble as the bubble gets bigger and bigger. So that's what it means. What we are currently here at the moment, we can imagine this as being a bubble and another bubble, and make sure the bubble is getting bigger and bigger and bigger and bigger. So we can imagine this as being this. Okay, so now if well, this bubble could be anything, this bubble could be anything, this bubble could be anything. I can call it B, 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 or I can call it C, 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 as C heads towards. But allow me to recycle the X. I'm just going to call this thing here X, X, and X. It's a different X from what we used right from the start. Right from the start here we used X. Well, our X here is a different X. So I do have the right to call this X. It's just a different X. So I'm recycling my X here. So you can imagine this as a bubble, as a bubble, as a bubble, as the bubble gets bigger and bigger. Okay, so now we are here. Okay, this thing here occurs in nature quite a lot. Whenever something grows by a percentage of an amount, and then you compound it continuously, for some reason this crops crops up. I will give you some examples. The example that I gave you in the past was a bank having an unrealistic 100% interest, and then you have to put $1 in here. In the future, it doesn't have to be 100%. It could be, I don't know, 7%, and you don't have to put $1 in there. You can put, I don't know, 873 or whatever. Okay, so we are now currently here. I will continue in the next video.